everyone. Today we will discuss about superconductivity. It's there in the syllabus in your BSc. So we'll have 3-4 classes about superconductivity. So this is the first part. I'll just will take around 15 to 20 minutes. We'll just discuss some basic things about how this superconductivity comes. Okay, so we'll just go one by one. So first of all, going to in superconductivity, let us talk about conductivity. We know about conductivity, isn't it? We know something about conductivity. Like if I tell you the range, the opposite of conductivity is the resistivity. We know that, conductivity. We generally give notation like sigma, and for resistivity we put a symbol like rho. Okay, so we have certain range. Like for insulator, the resistivity is order is 10 to the power minus 1, 10 to the power 3 ohm per meter. Sorry, not per meter, ohm meter. Similarly, for semiconductor, the range goes from 10 to the power minus 3 to 10 to the power 1 ohm meter. And for conductors, it's around 10 to the power minus 7 ohm meter. 10 to the power minus 7 resistivity, very small. Okay, so this is the resistivity. The thing is that how this resistivity comes. Why this resistivity we have in system? We have resistivity because of some kind of, we learned about those things in electrical conductivity, the drip velocity. Okay, or I can say, okay, what you know about drip velocity? So generally, drip velocity means when you apply some kind of electrical field, then those electrons are bound to go in a particular one direction. Then the average velocity is not zero, so you get the current in the system, isn't it? That is your drip velocity. Or if I write in terms of drip velocity, I will write I is equals to minus n e, number of electrons, the concentration of electron, the charge, and the average velocity. Suppose I am determining current in the x direction, then I will take the average velocity in the x direction. So if I talk about an isotropic system, now what is an isotropic system? Isotropic system means a system where all the physical properties are same in 3 directions. Suppose you have a system, any kind, suppose sodium chloride, a crystal. So since the superconductivity is a part of a condensed matter physics, and you have already studied about sodium chloride crystals and different crystals, let us consider about sodium chloride crystal. So if all the physical properties like refractive index, then you can say polarizability, dielectric permittivity, okay, all this resistivity, if all these things, the intrinsic physical properties are same in all the 3 directions like x, y and z, 3 direction x, y and z, then you say the system is an isotropic system. Okay, now there are 2 things, one is called homogeneous, one is called isotropic. Homogeneous means if the properties are same in the pointwise, in a system, in every point, if these physical properties are same, then the system is known as homogeneous system. And if the properties are same in the direction wise, like x direction, whatever is the refractive index, if it is same in the y and same in the z direction, then the system is known as isotropic system. Now here we are talking about a system which may not be anisotropic. It can be an anisotropic system. Okay, so suppose the average velocity, suppose the x direction, let us talk about x direction. Suppose the average velocity along x-axis is not 0. That means if you are applying some kind of electric field in the x direction, then the average velocity will not be 0. Whereas if you don't apply any kind of electrical field in the system, then the average velocity is 0, because the electron can go in all directions, all 3 directions are possible. So if you take the average velocity, which will be a 0, either in x, y or z, whatever. But at the moment you apply electric field, you get a drift current, means the electrons are bound to go in one direction. then the velocity, average velocity is not zero, then you get the drift current. Okay, while doing the calculation, we can derive that the conductivity is equals to Ne square tau by m, where n is the concentration, E is the charge, and tau and m is the mass. Tau is the important thing here. What is tau? Tau is the relaxation time, is the time between two successive collisions. Okay, suppose you have three electrons. Suppose you have a three electron, 1, 2, and 3. Suppose this electron collide with this after moving, suppose 2 seconds. Again this electron collides with this electron, further 2 seconds suppose. Then what is the relaxation time? Okay, so between this and this collision, second collision and third collision, sorry, the first collision and the second collision, the time gap there is known as relaxation time. Okay, so the idea is, if you increase the concentration of electrons, then you should have a higher sigma, no? Isn't it? But if you increase the concentration of electrons, that means you are increasing the number of electrons, the probability of collision will be higher. First thing, if the collision is higher, the relaxation time tau will be smaller, because this electron will frequently collide with another electron. That means sigma will decrease. That is the thing of the collision between electron and the electron. Now there is a chances, when you talk about solid, you have already studied about in crystal that there is a lattice points, basis, basis plus lattice give you crystal. So since in a crystal there are lattice points, so apart from this electron colliding with your electron itself, there are high chances that the electrons will collide with this lattice as well. Which, see, from the idea of simple harmonic motion or harmonic oscillator, you know that the vibrational energy is never zero. We have a formula like in the quantum, maybe you might have got this, n plus half h cross omega, I think, something like that, no? The vibrational energy, n is the vibrational quantum number. So vibration is never zero. Okay, so there will be always a vibration in any kind of system. Now in crystal or in the solid system, these lattice points, because we'll be working in some room temperature, there will be some kind of temperature, that means there is some energy, and these atoms will vibrate at those energy. Now why these atoms will vibrate in that vibrational spectroscopy? How this vibrational energy comes? See, we know about heat. What is heat wave? Heat wave is the wave whose frequency falls in the vibrational part of vibration, whose frequency falls in the infrared region, And in infrared region, we know about that the infrared region, the system, when the system vibrates with the vibrational energy, then its spectra falls in the infrared region. That means if the atom vibrates, or if the lattice points vibrates, they will vibrate with the energy equivalent to infrared energy. Okay. Now even at very room temperature, the system will vibrate. So if the system will vibrate, then those lattice points will vibrate, and those we come to know about a term called phonon. Okay, what is phonon? Photon is the quantum particle of light. Similarly, phonon is the quantum particle of vibration. You can say sound. Okay, if sound's a quantum particle, you can say the phonon. Okay, so phonon is a quantum particle for vibration. So since sound we say, heat wave we say, they all fall in the infrared regions. They are the same things. And these are the quasi-particles. Quasi-particles means you cannot take out the phonon outside. See, for photon, you have this photoelectric effect. So you might think that for phonon also we can have phonoelectric effect. No. Photon is not a quasi-particle, but phonon is a quasi-particle. Quasi means which reside inside the system, which cannot take out. So phonon is inside the system, and when the crystal vibrates, okay, they generate some kind of a phonon, and those phonons are always bound. If you consider like a particle, if you have a crystal, suppose, okay, these are the lattice points, suppose these are the lattice points, so they will vibrate like this, okay, and they will generate some kind of wave, and suppose these waves are the quantum particle known as phonon. Now this phonon, and the electron is here, no? Inside the solid, the electron is moving. This is the electron which is moving here and there. So these electrons will collide with this phonon particle, and that means there is a collision between electron and the lattice vibration, or you can say the phonon. So this is also one of the reasons for the resistivity in the system. As you increase the temperature, we know that resistivity increases. The reason is, definitely the number of collisions will increase between electron and electron. At the same time, as you increase the temperature, the vibrational energy of these lattice points will also increase. That means the energy of the phonon will increase, and there will be more numbers of phonon generation and more collision with the electrons. So the collision between electron lattice is one of the reasons because of which we have resistivity in a system. Resistivity is an internal property. Resistance can be changed, that's a different thing. So we are talking about resistivity, not resistance. Resistance depends upon just the word. R is equal to rho L by A. Simple. So rho is the internal property. R can be changed. If you change the L and A, that's a different thing. So the cause of resistivity is simple, that we have this kind of collisions. And suppose now you have created a system, you applied some voltage from outside, electric field, electrons are moving inside, you are getting the current, okay, no problem. Okay, you cannot go beyond particular value of current, there is saturation, all those things we already know. But as the moment you switch off the electric field or the whatever the potential difference you are using, the moment you switch off the system, the the current suddenly becomes zero. Okay, because though you have switched off, that means you have switched off the flow of electrons. Okay, you have switched off, and now the electrons will not get any kind of external energy, but the vibrations are already there, so the collision will be there. So electrons will keep on collide with these phonons and other electrons, and they are also at the same time not getting any kind of energy from the external source, so their drift velocity will become again zero. They will again start to move here and there, because after collision with the lattice, the phonon, which if you are applying electric field from outside, so even after collision with the phonon, they will again move towards along the electric field, okay, because of which we don't have a zero drift velocity. But the moment you switch off the electric field, now the electrons will show the property of collision, they will collide again, but now after collision, they don't know where to go, so they'll move in a random direction. So again the average velocity will become zero, no drift velocity, average velocity is zero, the current is zero. The moment you switch off the system, the electrons should go in that direction, but because of the collision, after collision they don't know which way to go. Okay, there is no direction for them, so ultimately the average velocity becomes zero, and you again get drift current as zero. So what happens if I decrease the temperature of the system? Somehow if I decrease the temperature, will this vibration relax, and will there be no kind of collision? If that happens, then I can make this resistivity very small. Okay, it's just a hypothesis I am saying. So they did with in the superconductivity, in superconductor, that's what we get there. What they tried suppose this is your resistivity, and suppose this is the temperature. Okay, they tried with the mercury. They tried with a mercury the metallic liquid. What they observe, that as the temperature is decreasing, resistivity is decreasing, at a particular temperature resistivity becomes 0. At this point resistivity becomes 0. Okay, so this temperature is around 4.12 Kelvin. It's Kelvin, not degrees Celsius. It's very small. It's minus 269 degrees Celsius around, very small. So at 4.12 Kelvin, they observed that the mercury's what is called the resistivity becomes 0. Okay, so this was a very new phenomena, and it was a very shocking thing, because 4.12 Kelvin the resistivity is becoming 0. So 0 resistivity, it's not, I think, 4.12, it's around 4.2. Just to check in your book, it may be 4.2 Kelvin. Okay, I'm just bad with the values. So the resistivity becomes 0. The moment resistivity becomes 0, that means if I make a circuit, they tried with the different system as well. Okay, let me tell you, they tried with different system, like aluminium, it was around 1.2 Kelvin. For lead it was 7.5 Kelvin. For tungsten it was 0.01, it's very small, Kelvin. For vanadium it was 3.5. These all are pure elements. Okay, they tried with some alloy as well, like niobium 3 and tin. This alloy, it was around 17.5 Kelvin around. These are called transition temperature. What is transition temperature? The temperature at which the resistivity becomes 0 for a system. Okay, so these are known as transition temperature. I can see critical temperature, TC, critical temperature, the temperature at which the system from a normal conductor becomes a superconductor. Because rho is 0 means superconductor. That means if I prepared a system of, suppose, aluminium, for aluminium is 1.2 na, 1.2 Kelvin. Suppose I made a system. Suppose this is my aluminium. I connected negative, positive, some resistance. Okay, let us move to the emitter here. Okay, so suppose I prepared a system with this is aluminium, and I took the system below 1.2 Kelvin. The moment I reach, suppose 1.1, 1.2 Kelvin, and if I switch off this battery, the current will be flowing in the aluminium for millions of years. Now, when I describe about this resistivity, when I switch off the system, the current becomes 0, because the collision was there between the electron but the collision between electron is not that significant, but the collision with the phonon was the main part. We used to play the main part of the resistivity. Okay, so here in the superconducting state, the moment I switch off the battery or the electric field, even after that the current will be flowing in the system, because the only reason that I could think of, because there is no collision. Because at this low temperature you might not have that energetic phonon which can collide with the electron and give you some kind of resistivity. That means if I get some, suppose if I apply electric field in a superconductor, and if I remove the electric field, till millions of years the current will be flowing in the system. There is no decay, because no reason of decay, because there is no resistivity. It's a very interesting thing, is that very interesting topic actually this is. Okay, so we know that we cannot make the vibrational energy 0, because it's n plus half, but at almost critical temperature, that means something is happening. Maybe the phonon's energy is very small, it's not able to collide with the electrons or whatever like that. But whatever is happening here, the phonons are there, but they are not colliding. or we can say that there is no inelastic collision between the electron and the phonon. That's why the resistivity is zero, and we are getting almost infinite current density. Okay, so the first thing that should strike our mind is if the rho becomes zero. Okay, if rho becomes zero, then what happens to our Maxwell's equation? Since we have studied in electrodynamics or whatever, electromagnetism, whatever you say, in earlier semesters, that we know about Maxwell's equations, the four equations that we have. The first one is comes from the Gauss law in electrostatics. So let us talk about that. No. The second one is from Gauss law in magnetism. Then we have the third law, which the third law is del cross E is equals to minus del B del T, isn't it? Where B is the magnetic field induced. Okay. Del cross C is equals to minus del B del T. Now we know that J is equal to sigma E. Okay. In terms of resistivity, what we'll have? J is equal to 1 by rho E, or E is equal to rho J, isn't it? So I can write like this. I can write like E is equals to rho J. E and J both are vector quantity. Okay, E is equal to rho J. Now if rho tends to 0, or if rho is equals to 0, which is happening in our superconducting state after critical temperature, if rho equal to 0, electric field is 0. If electric field is 0, then what about Maxwell's third law, third equation? E becomes 0. That means we will have this del B del T is equals to 0. That means the rate of change of magnetic field B will be 0. That means this B is either 0 or it is a constant quantity. That means magnetic field cannot change with time. This is interesting. Okay, the magnetic field, the magnetic flux, or B, cannot change with time, or either it can have 0 value or it cannot change with time. This is interesting. Okay, so since this Maxwell's law is not working here, so we might go for some different equations, and those equations are known as London equations. There are two equations, London first equation and London second equation, that we will talk about in the next classes. Okay, now so one condition we come to know about this, the resistivity zero. Then later Meissner also brought one condition, also showed one condition brought another property into the eyes of people, that suppose this is a normal conductor and we are applying magnetic field from outside. From outside we are applying magnetic field, so the lines of forces are crossing the system, penetrating the system. Okay, the moment the system brought at less than critical temperature, they found these lines of force are not able to, this is a straight line, these lines of force are not able to penetrate the system at T less than Tc. Okay, at T less than Tc. That means in the superconducting state, the magnetic lines of force are not able to penetrating the system. And if that is the case, then we know that the total magnetic field induced is equals to the applied, suppose H applied, plus you have the applied plus you can write mu naught m, isn't it? We can write like you have now B is equal to mu H plus m. Let me write in the different way. Mu H plus m. You have studied that thing. The total magnetic field induced is equals to applied plus how much the magnetic field generated by the system own. That is called magnetization. Somewhere you get intensity of magnetization, somewhere you get magnetization. Okay. So here B is 0. That means the total field induced inside the same material is 0. Isn't it? This one? There is no magnetic field inside the system. So the total is 0. That means this is equals to 0. Total means you understood, na? See here in this system B, this is the magnetic field induced total, okay, in total flux, which is equals to how much applied. These lines of force, some are because of the applied part and some are generated by the system by of its own. Okay, so M, capital M, the magnetization is for the created by own, and the H is the applied one, and B, which is known as the flux, magnetic flux, is the total. Okay, that's what you have written here. Total is equals to mu H plus M. The total is 0. Inside there is no magnetic lines of forces. The flux is 0. If that is the case, that means what? You have B is equal to 0. That means H plus M is equal to 0 because mu cannot be 0. Mu cannot be 0. So H plus M equal to 0, or you can write M is equal to minus H. Now susceptibility, we know that it is M by H, which is coming as minus 1, negative, and susceptibility is negative for a diamagnetic system. That means what? Are the superconductors diamagnetic? Isn't it interesting? That is, superconductors are diamagnetic. They are perfect conductor. The resistivity is 0. But at the same time they are diamagnetic. So this was discovered by Meissner, and the condition of this diamagnetism was brought by Meissner, and this is known as Meissner effect, that at superconducting state no lines of force can penetrate through the material, superconducting material, and this is known as Meissner effect. That means the superconductors are diamagnetic system. That's why when I was giving you the examples that scientists tried different material of calculating their critical temperature, none of the material was a magnetic material. I talked about aluminum, lead, tungsten, vanadium. None of them are in the bulk form. None of them are magnetic. Okay, because if you try to do with the iron, we'll talk about in the next class, then there is a difficulty because they are magnetic. So you might not satisfy the condition of this Meissner effect. So condition means now what we have? Now we have a scenario where rho is equals to 0 at below Tc. At the same time, the system is diamagnetic, perfectly diamagnetic. So we have two conditions for a system to become superconductor, both below Tc. That first it has to be a perfect conductor, that means resistivity is 0. Second, it has to be a perfectly diamagnetic system where all the lines of force are expelled, expulsion of lines of forces from the system. So these conditions are known as Meissner conditions. The second was put forwarded by him. In the next class, we'll talk about type 1 superconductor, type 2 superconductor, the variation of magnetic field and the temperature. All these things we'll talk about in the next class. For today,